Okay, just had lunch. Feel much better now. Okay, so now we're going to integrate x sine x. So what we have to do here is we have to decide what's u and what's v, or dv. So we're going to let u equal x. And then v, oops, I knew something was missing here. So u equals x, and then dv equals sine x dx. Now, if u equals x, then du equals dx. And if dv equals sine x dx, we want to find out what v is, so we integrate sine. And the integral of sine is negative cosine. Okay, so now we can plug in our integration by parts. So this equals uv, which is going to be negative x cosine x, minus the integral of v du. Oops, v du, okay. See, we've got uv times or minus the integral of v du. Now notice our integration just went from a difficult integration to an easy integration. So this becomes negative x cosine x minus a negative, so it just becomes plus, and integral of cosine x dx is sine x plus c, senor. That's it, game over. Now, the other way we could have done this instead of letting u be x and dv sine x dx, we could let u equal sine x, and then dv equal x dx. Okay, now, if u is sine x, then du would equal cosine x. And if dv is x dx, then that means v would be x squared over 2. Okay, so now we've got the integral of, oops, I'm sorry, cut, take 2. We'll edit that out. Okay, so we've got uv, so it's sine x times x squared over 2. And we'll just go x squared over 2 sine x minus the integral of v du. Okay, now, oh, you know what? If u is sine x, du is cosine x dx. All right, now, notice what happened here. When I went uv minus v du, it ended up being more complicated. See, the whole point of this is to make your integral simpler. But when the integral of v du is more complicated than the original integral, it went the wrong way. We don't do it that way. So, that's it, game over. Okay, so yeah, that's basically what the book was showing. Okay, so this is how you know how to do it, because if you do it right, it becomes simple. If you don't do it right, it becomes more difficult, so you do it the simple way. Cruising onward. The integral of natural log x dx. Now this has no options. What we do is we say, let u equal natural log x, and then dv equals dx. So I need the du and I need the v to get all my parts. So du, the derivative of natural log x, is 1 over x dx. And the v then would be the integral of the dx, which would be just x. So now I'm ready to do my parts. So this is going to equal uv, which is x times natural log x, minus the integral of v du. Look how nice and neatly that works. So this becomes x natural log x minus the integral of dx, which equals x natural log x minus, now this just becomes x plus c. That's it, game over. If you want to, you could factor out an x, but that's not necessary. Okay. Next example. X squared e to the x. Now, if we let, oh, we need to go red here. We let u equal x squared and dv equal e to the x dx. So that means du equals 2x dx and v equals e to the x. Now, we end up with uv, which is x squared e to the x, minus the integral of v du. Okay, so notice we still have a product here that we need to deal with. So we're going to do integration by parts again. This time we're going to let u equal 2x, and then dv equals e to the x dx. So that means I've got du equals 2 dx, and v is e to the x again. All right, so now my integral is going to equal x squared e to the x minus this integral. So I've got uv, so it's 2x e to the x, minus the integral of v du. So there's the integral of v du. Okay, so this is going to equal x squared e to the x minus 2x e to the x. Now, minus the integral of e to the x is e to the x, so this just becomes 2 e to the x plus c, senor. That's it. So you could factor your e to the x out. Yeah, watch how nice and neat this ends up being. So we've got e to the x times x squared minus 2x minus 2 plus c. And that's it. You can't factor that thing. Okay, let's see here. So we've got x squared e to the x minus 2x e to the x plus 2e to the x plus c. Now, remember, the c is a random constant, so technically speaking, when I did the first integral here, there should be a plus c here, and then when I do the second integral, I'm going to have a second constant, which could be c sub 2. But the fact that it is a random constant, it is just c. So that's it, game over. So notice you can do the integration by parts 2 separate times. Now, e to the x sine x dx. Now this one can be done, let me go back one more step real quick. Let's say instead of going let u equal x squared and dv e to the x dx, let's say we let u equal e to the x and dv is x squared dx. So notice if u equaled e to the x, let's just go over here and do that. All right, now, du, the derivative of v to the x, is e to the x. Now, v ends up being x cubed over 3. Notice that makes it more complicated instead of less complicated. So, the e to the x makes an excellent dv because when you integrate e to the x, it stays e to the x. But a polynomial does not make a good dv because when I integrate a polynomial, I end up with a bigger polynomial. So I want to use the polynomial as the thing that I'm taking the derivative of so that it gets smaller. Okay. Now, we have an e to the x and a sine x. Either one works for u and dv because when I integrate e to the x, I get e to the x. When I integrate sine, I still get a trig function. It's no more complicated. So I'll show you this both ways. So first, we'll let u equal e to the x and dv equals sine x dx. So that means du is going to be e to the x dx, and v is going to equal the integral of sine, which is negative cosine. So now, my integral becomes uv, so negative e to the x cosine x, minus the integral of v du, which is negative cosine x e to the x dx. All right, now let's just clean this up a little bit. So we have negative e to the x cosine x plus integral of cosine x e to the x dx. Now, we need to do this again, only we're going to go let u equal e to the x and dv equals cosine x dx. Okay, now du is e to the x dx, and v is going to be sine x. The integral of cosine is sine. So, now I have negative e to the x cosine x plus, now we need the uv, so it's e to the x sine x minus the integral of v du. So sine x e to the x dx, or we'll just go e to the x sine x dx. All right, now we're about to hit something tricky. Okay, what we're going to do is we're going to let the integral of e to the x sine x equal I. Okay, so we'll just put that right here. Let capital I equal integral of e to the x sine x dx. Now, watch the magic. Notice what I have. The integral of e to the x sine x dx, which is I, equals negative e to the x cosine x plus e to the x sine x minus I. Okay? Now, this I is what I'm trying to solve for. So what do? Well, I'm going to add I to both sides, so I have 2I equal negative e to the x cosine x plus e to the x sine x. And that means I equals 1/2 times negative e to the x cosine x plus e to the x sine x. And notice I did an integration, so I know the final answer has to be plus c. That's it, game over. Now if I want to simplify it, I could say, okay, integral of e to the x sine x dx equals e to the x sine x minus e, let's just do it like this. We'll factor out the e to the x. So e to the x times sine x minus cosine x all over 2 plus c, senor. That's it, game over. Let's see. Yeah, that's it. Now notice, we could have done the exact same thing if we had let u equal sine x dx, and then dv would be e to the x. Dv would, u equals sine x, and then dv would be e to the x dx. It would have worked out also. And But now the tricky thing here is we never actually evaluated the integral. What we did was we ended up with a cycle that brought us back to the same integral that we started with. Now once you get there, a lot of people would think, oh no, all is lost, we just got in an endless loop and we got nowhere. Well, yeah, we got somewhere. We basically ended up with an equation where all we need to do is solve for I. And so that's it. Okay. And lastly, the integral from 0 to 1 of inverse tangent x dx. Now this is your first case where we have limits of integration. So we have a definite integral here, not an indefinite integral. So watch how this works. So first, we're going to say let u equal inverse tangent x. Oops, rats. I blew a tire there. Let u equal inverse tangent x, and then dv equals dx. Okay, so now my du becomes the derivative of inverse tangent. Now, what is the derivative of inverse tangent? I'll wait till you get it. Okay, I know everybody got it by now. It's too easy. Okay, the derivative of inverse tangent is 1 over 1 plus x squared. And then v is just x. So now we're ready to spring into action. So this thing is going to equal uv, which is x inverse tangent x. Now remember, this is evaluated from 0 to 1 minus the integral of v du. Oh, and I forgot the du has to have a dx in it. Okay, so now we can evaluate this integral, and notice how are we going to do this? X dx here, well x is going to be, it's going to contain the derivative of the bottom. So what I can do down here is say let u equal 1 plus x squared, and then we go du equals 2x dx. And notice here's my x dx, so then I just say x dx equals 1/2 du. Now one other thing that we need to do is we have limits of integration here. So when x equals 0, what's u going to equal? 1 plus 0 squared. And when x equals 1, then u is going to equal 1 plus 1. So then this thing becomes x inverse tangent x from 0 to 1 minus, now we're doing u's this time, so I have 1/2 outside, because the 1/2 du is going to be the x dx. And then I'm going, instead of the integral from 0 to 1, x equals 0 to x equals 1, it's going to be u equals 1 to u equals 2 of, now, the x dx is already covered with the du, and now I just have 1 over u. Okay, so this equals x inverse tangent x from 0 to 1 minus 1/2. Now, this is natural log absolute value of u from 1 to 2. Now, really, the only time you need the absolute value is if it would be a negative number. 1 and 2 are both positive, so we really don't need the absolute value. So then I can just say, then this is x inverse tangent x from 0 to 1 minus, yeah, now what I can do is I can take this 1/2 and put it up here. So natural log of u to the 1/2. So let's just make it natural log square root of u from 1 to 2. All right, so this equals, put in the 1 here, and we have 1 times inverse tangent 1. Now, inverse tangent of 1 is, that means tangent of what angle equals 1? Obviously, pi over 4. So we have 1 times pi over 4. Now, inverse tangent of 0 is 0, and x is 0 too, so that's out. So this whole thing just becomes pi over 4 minus natural log of square root of 2 minus natural log of 1. Well, clearly natural log of 1 is 0, so we end up with pi over 4 minus natural log square root of 2. Bam! That's it. Game over. Okay. Now, if you wanted to, I went the other direction, but let's say we make this natural log of 2 to the 1/2, and then we make this okay, so the book shows it, make sure, what does the book do? Yeah, the book shows it like this. I actually think natural log square root of 2 is simpler. This is easier to get a decimal approximation. So that's it, game over. Have fun with these.